Let's look again at this situation where a source is connected to some length of transmission line. Again, we are not stating what is connected at the end of the line, what the load is. We want to analyze simply this structure that we have here. And in this structure that we have here, a source with a lossless two-port device, that lossless two-port device being the lossless transmission line. That structure is a one-port device, which is a source in itself. What we can view this structure as a two-port device, which is a source transformer on the original source. When we connect the two-port device to this source, it will come up with a new equivalent circuit, a new equivalent source. And the question is, what will that be? Now, this is why I put the gray box around the source here at the beginning of the transmission line. That source, VG and ZG, are an equivalent source to some useful device that the transmission line has been connected to. So we don't want to view these as two physical devices. There's not literally a ideal voltage source connected to in series to a source impedance here. Rather, this is simply an equivalent circuit to some useful device, and we've connected some transmission line to it. And ultimately, the question we ask ourselves is, what is the equivalent circuit now of this entire structure? So the equivalent circuit is shown here. Again, we take our original source, which is really an equivalent circuit to some useful set of devices here. We connect a lossless transmission line, a link the transmission line, which is a two-port device to it. And we can look at this transmission line then as a source transformer that transforms our original source into a new source. This is the equivalent circuit for the entire circuit structure behind it. The source with a transmission line can be written as an equivalent source of this form. Now notice the transform source is very different from the original source. V out is not equal to VG. It doesn't have the same magnitude, generally speaking, and won't have the same phase, generally speaking, from one to the other. Likewise, Z out is different than ZG. Both the real and imaginary parts of these two source impedances are going to be very different. Moreover, we can't really say anything about the relationship between those values. I can't say that the magnitude of V out will be either greater or less than VG. It depends on the values. It depends on the transmission line and its length. The question then becomes how to determine these values, V out and Z out, the new equivalent circuit for a original source that's transformed by a length of transmission line. We can use our definition of Thevenin's equivalent circuits, where we could go through and put a short circuit and an open circuit at the end of the transmission line and apply boundary conditions and find the solutions for each, and from that determine the Thevenin's equivalent for V out and Z out. Another way of doing it may be a little bit easier. Earlier we found that if we knew the impedance matrix of a two-port device, if we knew all the trans impedance parameters, all four of them for that two-port device, then we knew that we could write the transform source from VG and ZG into a new source of V out and Z out by using those transimpedance parameters. The transimpedance parameters in ZG and VG would then map into a new equivalent source with a V out open circuit and a Z out source impedance. Of course, to accomplish this transformation, we would need to know what are the transimpedance parameters of a length of transmission line. Now, we haven't talked about that. We've talked about a lot of impedances associated with the transmission line, the characteristic impedance, the line impedance, the input impedance, the load impedance. But what we haven't discussed thus far is the transimpedance parameters of a transmission line. A length of transmission line is a two-port device, so it can be, and it's linear, so it can be characterized by a 2x2 impedance matrix. So what are the elements of that matrix? It turns out it's not really too hard to find. We're 90% of the way to the answer. Because recall the method or definition of a transimpedance parameter was to first go through and put an open circuit at one point, port rather, and then determine the two voltages, in this case V1 and V2 rather, in terms of current I1. I2 is equal to 0 because we put an open circuit here. And so we need to find the voltage here at the open circuit output and the voltage here at the input in terms of I1. And you may say, well, gee, how can I do that? How do we determine that answer? We've already determined that answer. Remember, this is one of our special cases. We talked about a terminated transmission line, and this is what we have now, a terminated transmission line. The load termination that we have that terminates the line, in this case, is an open circuit. And that was a special case. Go back and look. We talked about what happens when we terminate a transmission line in an open circuit. We talked about what the current was, the total current was along the transmission line, and we talked about the total voltage along the transmission line. And from that total voltage, therefore, we can determine the value of V2, and we can determine the value of V1, and from that we can determine the transimpedance parameters. Since the load is an open circuit, we know the corresponding gamma the corresponding gamma L is equal to 1. And since we've written this in this case as Z equal to 0 being the location of the load, we can write the total voltage in terms of gamma L with the value of 1, and the result is this. And if you recall, again, that was a result we had for a special case where we terminated a transmission line in an open circuit. The total voltage, it was a function or proportional to the cosine of beta Z. Likewise, for the total current, for the value of gamma L equal to 1, we found that the current along a transmission line terminated in open circuit had this form. Again, go back and look and see. We can use directly those results. Well, since we know the voltage at everywhere on this transmission line terminated in open circuit, that means we know the voltage at the input and at the output over here. Now this actually should be V1, not V2. V1 here and V2 here. Likewise, we know the current at everywhere on the transmission line. We know the value of I1, or we can determine it, and we can determine the value of I2. And if we do, we find it will be equal to 0, and that passes the sanity check. So let's go through and find those values. V1, the voltage right here, we evaluated at an index of minus L. Z is equal to 0 is where the open circuit is. Z is equal to minus L. Here is in the input. And so the voltage at this location at the transmission line by KVL is equal to V1. Again, that should be V1. And there is the result once we insert minus L. I1, the current here at the input. Again, we take our total current expression and evaluate it at minus L, and we get this. And then finally we go to the voltage V2 at the other end, and that is the voltage at the end of the transmission line. The voltage across the open circuit, we evaluate it as Z is equal to 0, where the open circuit is, and we simply get a value of 2 times the complex wave amplitude, V0 plus. So again, V1, V2, and I1, and those are the values we need to determine Z11 and Z21. The transimpedance parameter Z11, of course, is the voltage at port 1 divided by the current at port 1 when the current at port 2 is equal to 0. And of course, since the port 2 is terminated in an open circuit, we know I2 will be equal to 0. And so we find the voltage V1 and I1 under that condition, and we find the resulting transimpedance parameter Z11 is equal to minus J Z0 cotangent of beta L. Likewise, for a Z21 transimpedance parameter, the ratio of V2 to I1 when I2 is equal to 0, and similarly we find this result for that transimpedance parameter. Now, we could go through and do this again for Z22 and Z12, where we put an open circuit on port 1 and determine the current at port 2, for example. But what we find is the symmetry of the structure. If I take a transmission line and flip it around, I get the same structure. What is Z1, what is port 1 and port 2 is completely arbitrary. And so we can apply symmetry to conclude that Z22 is equal to Z11, and likewise Z21 is equal to Z12. Again, if we flip it around, we have the same structure. We'll talk more about symmetry later in the course, but this is one of the benefits of analyzing a perfectly symmetric circuit is we only have to analyze half of the, in this case, transimpedance parameters. So we put our results together, and this is the impedance matrix of a lossless transmission line of length L. Notice nowhere in here do we care about our indexes. This is a physical statement, so it can't depend on how we define the location of one in the line or the other. It simply depends on the length of the transmission line, L, as well as its characteristic impedance, Z0. Now, one thing we notice about each element of this impedance matrix is that each element is purely imaginary. There is no real part. The real part of all four elements are equal to 0. And is this a coincidence? Is this a surprise? And hopefully it's not. In fact, this is a sanity check on our analysis, because a lossless transmission line is, of course, lossless. It has no resistive component. It is inductive and capacitive purely, and therefore we know a lossless device without any resistance must always have transimpedance parameters, which are all purely imaginary. It can have no real part. If there's a non-zero real part of any element, that implies that somewhere in that circuit there is some resistive element that can absorb energy, and that is not true for lossless transmission lines. So again, this passes the sanity check. It doesn't surprise us that the transimpedance parameters are purely imaginary. In fact, it gives us some sense of relief that we have, in fact, done the analysis correctly. We now go back to the problem of our transform source. We take a source, or at least the equivalent circuit of some useful device, Thevenin's equivalent, VG and CG, and we attach to it a length of transmission line, and that creates a new equivalent circuit. We can look at the transmission line as a two-port device which transforms our original source into a new source with values V out and Z out. What are those new values, and how do they relate to the original values VG and ZG? Well, we had an expression in terms of the transimpedance parameters of a two-port device, and now we know the transimpedance parameters of a length of transmission line. We simply insert the results we got for the transimpedance parameter analysis into this expression, and this will give us now the result for V out, this voltage here, and likewise for Z out, this result for this output impedance. Again, we notice that Z out is clearly not equal to ZG. ZG is part of the relationship, but it's not the only part. V out is not equal to VG either. Again, VG is part of the relationship between that expresses V out, but there are, of course, many other elements as well. If we look at those other elements, we see they involve every piece of the circuit. If this is an equivalent circuit, V out and Z out, for this entire structure, it needs to include, comprehend, every parameter that defines this entire structure. Well, what are those parameters? For the original source, clearly it's VG and ZG. For the transmission line, it is the physical length L, or more specifically, the electrical length beta L, along with the characteristic impedance Z0. And when we look at these results, we find all of those parameters map into the equivalent circuit. We look at these and we find they are dependent on Z0 clearly, beta L clearly, ZG clearly, and VG clearly. So it passes the sanity check that our transform source depends on every element of the entire circuit, because this transform source is the equivalent circuit for this entire thing, and thus it must include a description of each and every element in that circuit that it is equivalent to. We know then that the transformed open circuit voltage Vout is different than VG, different magnitude, different phase. And Zout is different than the original source impedance ZG, different real part, different imaginary part. Everything seems to be transformed by this length of transmission line. Nothing stays the same as it was before. But let's ask ourselves about available power. Will the available power of the transformed source be different from that of the original? This is a question we've asked before, earlier, and we know what the answer is. Because our transmission line is a lossless two-port device, the available power of the transformed source must be equal to the available power of the original source. A lossless two-port device cannot either increase the amount of available power in the transformation, only an active circuit can do that. A lossless two-port device cannot decrease the available power. Only a lossy device, one with transimpedance parameters that have a real component, only they can do that. Since we have a lossless two-port device, the available power of the original source and the transformed source must be identical. And so we can take the available power of the original source, and we know that equals to the magnitude squared of VG divided by 8RG, and we can take the available power of the transformed source, that being the magnitude squared of V out divided by 8 times R out, the real part of the of Z out there, and we find that those two values must be equal to each other. This is an invariant statement, a statement that whatever we do with the transformation using a lossless two-port device, these values must remain equal to each other. We've just then done the analysis for the transformation of some general source to a new equivalent source where the transformation is done by a lossless length of transmission line, a lossless two-port device. Now let's go and look more specifically at a special case of our original source. Let's say our original source is the quote-unquote match source, a source whose source impedance is numerically equal to the characteristic impedance to which it is attached. Again, this does not imply anything about a conjugate match. Conjugate match could happen with a match source, or it may not happen with a match source. They're independent. The fact that they both have the word matched in their terminology does not make them equivalent in any way. If you go back and look at our expression for the transformation of the original source VG and ZG into a new source Vout and Zout, you look at the math and it was fairly ugly with trig functions and the like in there, a lot of work that would have to be done to find the calculation. But for this special case where ZG happened to be equal to Z0, and you should go back and do that, insert that for that case. Do a little algebra, things tend to fall away, simplify down, to the point that the transform source, if the original source were a match source, the transform source can be written very simply. First of all, if we have a match source that is transformed by length of transmission line, physical length L or electrical length beta L, we find that the resulting open circuit voltage Vout is related to the original open circuit voltage VG in a very simple way. It's simply VG times the complex exponential e to the minus j beta L. In other words, the magnitude of the original open circuit source VG and the magnitude of the transform source Vout are exactly the same. The magnitude of the two sources do not change if the transmission line is transforming a quote match source with a character of the source impedance of Z0. The only thing that changes is the phase of those open circuit voltages, and they change by a phase that's precisely equal to the electrical length of the transmission line that is doing the transformation. Even more simply, we find that the new output impedance is equal to the characteristic impedance of the transmission line, more specifically equal to the original source impedance if we have a matched source. So our math for the transformation of a general source into a new source with the length of transmission line, again, is a little bit messy. But if that original source is a matched source, its source impedance is numerically equal to the real value Z0. The original source impedance is Z0 plus J0, in other words. Then the transformation of length of transmission line is trivial. The impedances stay exactly the same real part of Z0, and of course the imaginary part then would have to be 0. And the transformed source voltage is precisely the same magnitude. The only difference is a phase shift of precisely the electrical length beta L. Perhaps most importantly in this transformation of a matched source is the statement that Z out is equal to Z0. We have a matched source, so the source impedance is Z0. We put a length of transmission line in front of it to transform the original source into a new source, and that new source likewise has a source impedance of Z0. And the most important thing about this is that is true regardless of the line length L. The relationship between the original source impedance and the transformed source impedance is independent of that length. In both cases, they're equal to Z0, period, regardless of the length of that transmission line. And the phrase, regardless of line length in microwave engineering, is one of the happiest phrases a microwave engineer can hear. The fact that a result is independent of the transmission line length connecting devices makes the job of a design engineer, a microwave design engineer, much easier. And so things like matched sources, for example, that have this characteristic, this very simple transformation from the original source to a new source, is quite desirable, particularly when that transformation is independent of that transmission line length.